All right, so this is section 2.3. It's called Properties of Functions. We have 7 learning objectives. You don't have to write them all down now. We'll write them down as we hit each one. The first one that we're going to look at is determine even and odd functions from a graph. So go ahead and write that on your paper. All right, and if you're watching this video or with me in class, go ahead and box the word even and the word odd, because those are some vocab that we're going to discuss and are important to our notes. All right, a function is even if for every number x in its domain, the number negative x is also in it. So this is really similar to our symmetry test that we did last chapter. A function is odd if for every number x in its domain, the number negative x is also in the domain. And this is also like the test for symmetry we did last chapter. A function is even if and only if its graph is symmetric with respect to the y-axis. Remember from last chapter, we did that symmetry test, and this is the same process as our y-axis symmetry. And our odd function, so a function is odd if and only if its graph is symmetric with respect to the origin. So if you look at the odd function, it is that origin symmetry test. So right next to your even and odd functions, go ahead and write y-axis symmetry and origin. Okay, so we're going to take a look at 3 different figures and determine whether they are even, odd, or neither. All right, so A is an upside down parabola, so my coefficient is going to be, for my parabola equation, is going to be negative. But you look at the graph, and is it even, odd, or neither? What do y'all think? It is even, and it's not odd. And can you be both? Can you be both even and odd? It's, yeah, I right now I can't think of a scenario. I will update you.
If it was one of those functions that go like that, and then there's another one.
Yeah. What about like a circle?
Parabolas. Oh, yeah.
Or a hyperbola, the 2 parabolas. I can see that as well. Yeah, so I would say right now, circle kind of is the only one that can qualify for both. All right, so A is even. So write that below your graph. B looks like a little modified swimmer, but he is above, kind of above the, all of his curves happen above the x-axis, and he is a case where it's neither, because to have origin around the symmetry around the origin, it is what happens in quadrant 1 has to happen in quadrant 3, and we're not getting that for this. So under that we put neither, neither, potato, potato. All right, so then we look at this nice little squiggly graph. And he is, so for C, it's odd because it has symmetry with respect to the origin. What happens in the first quadrant also happens in the third quadrant. So go ahead and write odd underneath that picture. Okay, so that's looking at the graphs. That's how to determine if it's odd or even or neither. And now we're going to identify odd and even functions from the equation. So we're going to do the algebra on that. And I personally like this much better than trying to identify it from the graph. But I am in love with algebra. Don't tell anybody, especially my husband. So we're going to identify even and odd functions from the equation. So go ahead and write this learning objective, and once again put a box around even and odd, because those are the important terms in this section. All right, we're going to take 3 functions and determine whether they're odd, even, or neither. All right, so for the first one, we're going to do our even test. And this is a parabola, so I kind of already have a good idea how this is going to come out. If I put a negative value in for x, so the graphing utility shows us that it is a parabola, so it has symmetry with respect to the y-axis, and we're going to plug in negative x for our regular x, and if we get out an equivalent statement, then we know that it is even. So we go negative x times negative x is x squared minus 5. So we know f of negative x is also equal to the same thing as f of x. So that verifies what we see from the graph. It is even. If you look at B, B is a swimmer, and he is moved down 1 unit. That's what that -1 does. And so we can't, from this graph, we can't say yay or nay. So we're going to do a little test. So we're going to plug in. We don't definitely know it's not y-axis just from look. We can use both the graphing and the algebra to make our process a little quicker. So I'm not going to even test it for being even because it is not symmetric with respect to. So if we replace x, negative x for x, and we cube it, we get negative x cubed minus 1. We look at the opposite of g of x. The opposite of g of x would have been negative x cubed plus 1. That is not the same as what we got when we did our symmetry test. So we know it's not even. We know it's not odd either. So this one is neither even nor odd. All right, so let's take a look at h of negative x, and we'll compare it to its original equation. All right, so when we put in that negative x and cube it, we get negative x cubed. We're going to put that negative in front of the 5. So we get negative 5x cubed minus a negative is plus. We can see that this is the opposite of our h of x that we start out with. It was positive 5x cubed minus x. Now it's negative 5x cubed plus x. So we can say that it is the opposite of h of x, which means that C is odd. So now we're going to use a graph to determine where a function is increasing, decreasing, or constant. This is mega easy. You guys got this. Just looking, finding it increasing, decreasing, or constant. All right, so after you write the learning objective down, I want you guys to write down this terminology, because when you move on to learn more math, they're going to use more of this terminology and expect you to spit it back. Like when we did interval notation, knowing closed interval, open interval, what's and how to phrase things in a mathematical way. So I'm encouraging you to write this down. Just as it's written here, and on the side you can write down the version of it that makes sense to you, which is what I would definitely recommend. So a function is increasing on an open interval I if for any choice of x1 and x2, with x1 being smaller than x2, we have f of x1 is less than f of x2. So when we plug in x1, if we have an increasing function, it's going to give us a smaller value than when we plug in x2. That's the real version. Let me pause it. So make sure you include the pictures of increasing, decreasing, and constant values in your notes. Function f is constant on an open interval I if for all choices of x in that interval, the values of f of x are equal. All right, so we're going to go a little bit bigger because the previous information was more like an algebra 2 kind of terminology, but now we're going to evaluate functions a little bit more closely and look for local maximum and local minimums. So a local maximum happens if for an interval containing c that f of x is less than or equal to f of c, then f of c is a local maximum. It's kind of like a little hill in your function. So it's right at the top of that hill. That's your local max. And a function has a local minimum at c if on the open interval that for all x in our interval, f of x is bigger than f or equal to f of c. So that's like a little valley on your graph. That little valley is going to be your local minimum. So all of your function values on your interval are going to be bigger than your local min. So let's see how that looks. If you guys look at example 4. So we're going to go ahead and sketch figure 24 in your notes, and we're going to take a peek at how to find the local maximum and the local minimum for figure 24. Okay, so we need to, for figure 24, we're going to see for any values of x, does f have a local maximum? So we want to find the top of our hill. And then we're going to list those local maximum values. So if you're looking at this graph, the hill happens at 1, 2. So at 1, 2, that's considered a local max. And then B, at what value of x, if any, does f have a local minimum? And list the local minimum values. So we have two minimums here. So from negative infinity to 0, we have a local min at negative 1, 1. And from 0 to infinity, we have a local min of 3 at 3, 0. So the x values that have a local minima are negative 1 and 3, and they happen at f of negative 1 is 1 and f of 3 is 0. And let's look at our increasing, decreasing intervals. So if we look at figure 24, it's increasing. So if I'm going, just looking at increasing, so from -1 to 1, we're increasing. And from 3 to infinity, we're increasing. So we are going to go, the intervals look like parenthesis -1 comma 1, close parenthesis, and 3 comma infinity. You can also write it as -1 less than x less than 1, and x greater than 3. And then we are decreasing, so we're decreasing from -infinity to 1, and from 1 to 3. And if you look, please note that when you're doing it in interval notation, it is a open parenthesis because you're not including your local min or max x coordinates in that increasing or decreasing interval. Because at that point, you're changing directions, and so you're neither increasing nor decreasing. So keep those intervals open. All right, fifth learning objective. Use a graph to locate the absolute max and the absolute min. So these are different. You guys did the Quizlet for chapter 2. These are different than a local max and local min. Without knowing anything, without even touching those definitions, what do you think the difference between an absolute max and min and a local max and min is going to be? All right, so absolute maximum. So if there is a number u in our interval for which f of x is less than or equal to f of u for all of our x's, then f of u is the absolute max. And we say that the absolute maximum of f occurs at u. If there is a number v, so that f of x is greater than or equal to f of v for all of the x's on our intervals, then f of v is the absolute minimum. And we say the absolute minimum of f occurs at v. So if you look at this little picture, please note this function doesn't go off into infinity in the negative x direction or off into infinity in the positive x direction. This function is restricted from a to b on our x-axis. We can do that because we are the all-powerful math wizards. So we can restrict a function and just write one that goes from a to b. And in this case, so our domain is from a to b included, and our absolute maximum is at this u value for x, so it's at f of u, and our absolute minimum, where nowhere else on our graph is it this low, is at v comma f of v. So this is the picture version of these words. All right, so we're going to sketch these little graphs, and I found this fascinating because it is not intuitive where all these, because there's some holes in here, there's some changing in directions, the interval is, the intervals go in certain ways. Some of these are piecewise. So we're going to go ahead and sketch graphs A through E on our paper. So go ahead and pause the video and do that. No, it's not. Okay, so if you guys look at A, the absolute max is at 3, 6. So I think it's this point here.
No, it's not.
It's not.
Way too mathy for me.
Oh, 3, 6 is higher. 3, 6 is higher. My graph has this a little lower. So 3, 6 is the largest f of x value on our graph, and our absolute min is at 0, 1, which is this bottom point here. So even though it's got a little valley here on the right-hand side, that little valley is not the absolute minimum. It's actually the smallest coordinate in our function. So our absolute max for our B is the 5, 3, because he is the largest output value. And it does not have an absolute minimum because there is a hole at 3, 1. When there is a hole where your minimum should be, then you have no absolute minimum.
Because it's a rounded curve, there is no point.
Right, so there are an infinite amount of points that lead into, from either side, 3, 1. And there's not one that is lower than the other on either side. So you can't say, my absolute min is 3, 1, because there's a hole there. So for C, our absolute max happens at 5, 4. And our absolute min is 1, and it's our little constant function. So because we're at 1, between 1 and 2, that whole section of that constant function inside is our absolute minimum. So all those points in there. For D, we do not have an absolute max because it goes on forever to positive infinity, but our absolute min is at 0, 0. And then for E, there is no absolute max and there is no absolute min, none and none. And I think these are the craziest scenarios you will probably ever see when we're determining absolute max and absolute mins. I in all my years have never encountered anything as crazy. All right, so let's read through the extreme values together. If f is a continuous function whose domain is a closed interval a to b, then f has an absolute minimum and an absolute max on the interval a to b. So if you are continuous, no holes or craziness going on, then you must have an absolute max or an absolute min on your interval, or absolute max and an absolute min on the interval from a to b. All right. This is the easy part, using a graphing utility to approximate local max and local min and determine where a function is increasing or decreasing. So the first thing you need is a graphing utility. So pull out your graphing calculator. I pulled out my Desmos on my computer. All right, so it says use a graphing utility to graph f of x equals 6x cubed minus 12x plus 5 for negative 2 less than x less than 2. Approximate where f has a local maximum and where f has a local minimum. So what you want to do is put this function 6x cubed minus 12x plus 5 into your graphing utility and then set your window to match the interval. So x min would be negative 2 and x max would be 2. All right, so between negative 2 and 2, I have a local maximum here at negative 0.816 and for my x value and 11.5 for my y. I have a local min here at 0.816 for my x and negative 1.5 for my y. And then if you look, increasing or decreasing, so from negative 2 all the way to here, negative 0.816, I am increasing. I'm also increasing from 0.816 to 2. And then I'm decreasing from negative 0.816 to positive 0.816. So go ahead and on your graph, put your local max and local min. These ones have identified the intercepts as well. That's definitely not necessary. And then put plus signs where it's increasing and minus signs where it's decreasing to indicate which intervals you're increasing and decreasing on. All right, average rate of change function. The only thing that you have to really keep track of with average rate of change is your algebra. If you get lost in the algebra, this is going to be a very difficult situation, but other than that, it's really easy. Okay, so if A and B, as long as they're not equal, are in the domain of our function, the average rate of change of our function from A to B is, and then this is what I want you to write here, average rate of change equals delta y over delta x. When you see a triangle, whether it's in science or math, that is the Greek letter delta, and it means change. So the change in y is our function when we have b input into it, minus our function when we have a input into it, and our change of x is b minus a, as long as a and b are not equal to each other. So we are going to evaluate the average rate of change for our function f of x equals 3x squared. And the first interval we're going to do it from is from 1 to 3. So a is going to be 1 and b is going to be 3. So we plug in 3 into our function and 1 into our function. When we plug in 3, 3 squared is 9. 9 times 3 is 27. When we plug in 1, 1 squared is 1 times 3 is 3. And then b minus a would be 3 minus 1. So 27 minus 3 is 24, and 3 minus 1 is 2. So the average rate of change from 1 to 3 of our function is 12. So all this is algebra, plugging numbers in, calculating and evaluating, and getting the value out. We do the same thing, except we change from a 3 to a 5. So we're now going from 1 to 5. So we put 5 into our function. 5 squared is 25. 25 times 3 is 75. Minus f of 1, which we found to be 3 last time we calculated it. And then 5 minus 1 is 4. So 75 minus 3 is 72. Divided by 4 is 18. We're going to do this one more time from a equal 1 to b equals 7. And remember, f of 1 was 3, f of 7. 7 squared is 49 times 3 is 147. And then you got 7 minus 1 on the bottom. We get 144 divided by 6, which is 24. So the average rate of change, as long as a and b are numbers, will be a number. All right, so there is a little formula for the line that is secant to a function at a point. So the secant line is equal to f of b minus f of a over b minus a. That should be pretty familiar. That's our average rate of change function, but we're going to change it up just a little bit, and we're going to say f of a plus h minus f of a, so we're replacing b with a plus h, divided by h. So write this part down. And all we're going to do is apply our function operations and plug them into this secant line formula.